Humans are incredibly mobile creatures. We always seem to be on the move. There's hardly a place on our small sapphire sphere that we can't travel. To assist us in traversing our planet, we have conjured up a convenient coordinate system. The Earth's surface is divided into an angular grid system of latitude and longitude. Latitude lines extend from the equator to the poles. The equator is 0 degrees latitude. 90 degrees north takes us to the North Pole. And the South Pole is 90 degrees south. Lines of longitude circle the world east to west. By international agreement, longitude starts on the prime meridian, which runs through Greenwich, England. The prime meridian is 0 degrees longitude and is measured to 180 degrees eastward and 180 degrees westward. That 180-degree line on the other side of the world marks the international date line, which runs through the middle of the Pacific Ocean. Each degree of latitude and longitude are several kilometers wide. To increase precision, each degree is subdivided into 60 minutes. And each minute is further divided into 60 seconds. Say you wanted to know the coordinates of Washington, D.C. You would measure 38 degrees, 54 minutes, 17 seconds north of the equator, and 77 degrees, 0 minutes, 59 seconds west of the prime meridian. This is how we have gotten around our tiny world for the last couple of hundred years. Well, maybe you haven't. When was the last time you gave someone your location by latitude and longitude? That's something we don't normally do, but your smartphone does. Your phone knows your location and can get you from point A to point B just by asking. So, who needs to go through all the trouble of figuring out latitude and longitude? This bit of modern magic comes from the sky. A constellation of navigation satellites can show your location just about anywhere. Everything is fine as long as your batteries hold out. But if your phone dies, or even worse, the satellites fall out of the sky, what could you do? You could still look up. This is nothing new. People have been using the sun, moon, and stars to get around for as long as people have been getting around. To assist you in finding your way around the sky, a few points of reference are necessary. To find out where you're going, you need to know where you are. We'll start with the point right above your head. In astronomical parlance, this is called the zenith. This is specific to your location. Someone several kilometers away will have a slightly different view of the sky. 90 degrees down from the zenith is the observer's horizon, which is also specific to your location. Knowing your directions would also be helpful. For those living in the northern hemisphere, this is relatively easy. Just find the North Star. Polaris, which just happens to be the star in the end of the handle of the Little Dipper, is almost directly above Earth's North Pole. To locate Polaris, use the bright stars of the Big Dipper. Draw an imaginary line between the two stars that make up the end of the bowl of the Big Dipper. Extend that line into space until you come to a fairly bright star, and you will be looking north. If you're facing north, then south would be behind you. That would make east to your right, and west would be to your left. Astronomically speaking, these are called cardinal points. Another use for Polaris is estimating your latitude. If you measure how high Polaris is above the horizon, you will have some idea how far north of the equator you happen to be. You don't need any fancy equipment, just your hand at the end of your arm. If you make a fist and hold up your hand at arm's length, that covers about 10 degrees of the sky. We know that Washington, D.C. is at 38 degrees north. So if we look at Polaris above the U.S. Capitol, it's almost 4/5 above the horizon. There's one last line of reference we use on a daily basis. But many may not be that aware. That would be the observer's meridian. Imagine a line extending from the south through the zenith toward the north, dividing the sky in half. This becomes relevant when the sun enters the picture. After the sun rises, it appears to move toward the meridian. In other words, it could be said that the sun is before the meridian. In Latin, the word for before is ante. So the sun is ante-meridian, or AM. When our star reaches the meridian, it's at the highest point in the sky. Some refer to this as high noon. Then the sun moves away from the meridian, thus after the meridian. Post is the Latin word for after. The sun is post-meridian, or PM. All of these points of reference are particular to your location. Say you look and see a bright star on your meridian. You call up a friend who lives several kilometers to your east and ask, "What is that bright star on the meridian?" Your friend won't be sure what star you're asking about, because from your friend's location, that star has moved past the meridian and is on its way to setting. Wouldn't it be helpful if there were some kind of coordinate system for the sky that was independent of your location? A scheme where each object in the heavens had its own particular position. Well, there is. Imagine the latitude and longitude lines stretched into space. A spherical grid spanning the entire sky with Earth at its center. There's a snappy name for this out-of-the-world orb, the celestial sphere. Many of the lines of reference may sound familiar. They only have different names. The Earth's equator becomes the celestial equator. Instead of latitude, we have declination. The celestial equator is at 0 degrees declination. Declination extends north and south of the celestial equator until you reach positive 90 degrees, which is the north celestial pole, and negative 90 degrees, which is the south celestial pole. Both of these points hover above the Earth's poles. Notice how close Polaris is to the north celestial pole. The lofty longitudinal equivalent is right ascension. Because these lines of reference have to take into account the Earth's rotation, they're not measured in degrees, but hours. Guess how many hours of right ascension there happen to be on the celestial sphere? If you thought 24 hours, you win a moon pie. To locate the celestial version of the prime meridian, we're going to have to introduce one more important line of reference. And to get a handle on the starting point of the right ascension, a quick trip through the solar system is in order. From the perspective below the Sun and just outside the orbit of Neptune, you may notice that the paths made by the planets appear roughly circular. As we start to move back home, you'll see that the parade of planets is positioned in a particular path in relation to the Sun. The solar system appears as a flattened disk with the Sun at the center and all the planets moving around it. This almost two-dimensional appearance has led to the term plane of the solar system. In the skies of Earth, the plane of the solar system materializes as an arc across the heavens. The Sun, Moon, and planets move along this pathway called the ecliptic. It's the position of the Sun along the ecliptic that relates to the starting point of right ascension. When we bring the celestial sphere back into the picture, you'll notice that the ecliptic doesn't line up well. In particular, look at the celestial equator and the ecliptic. These two cosmic circles are tilted to each other by 23.5 degrees. If this number sounds familiar, that's because this is the Earth's tilt in relation to the Sun. The celestial equator and ecliptic intersect at two important points. Twice a year, the Sun is positioned directly above the Earth's equator. At these times, there are mostly equal periods of day and night. These are the equinoxes, which in Latin means equal nights. Those intersection points on the celestial equator and ecliptic mark the equinoxes. It's the spring or vernal equinox when right ascension begins. In other words, the vernal equinox is 0 hours of right ascension. 6 months later, when the Earth is on the other side of the Sun, we see the fall or autumnal equinox. And you may guess, that would be at 12 hours of right ascension. Like latitude and longitude, declination and right ascension are farther divided into minutes and seconds. Each degree of declination has 60 minutes, and each minute has 60 seconds. As well as each hour of right ascension is broken down into 60 minutes, and in turn, 60 seconds. Now, when you call up your friend and ask about that star, you can give a specific location. You can ask, "What's that star at 6 hours, 45 minutes, 8 seconds of right ascension, and negative 16 degrees, 42 minutes, 58 seconds of declination?" Your friend might respond, "Oh, that's Sirius, the brightest star in the night sky." As helpful as the celestial sphere is in finding things in the sky you can see, it's really handy for locating things you can't. There's an entire universe just beyond unaided eyesight. These distant denizens of the cosmos come into sharper focus through the lens of a telescope. With the celestial sphere and a well-aligned telescope, you could find nebulas, clouds of gas and dust where stars are sparking to life, open star clusters where young stars slowly drift away from their nebular nurseries, planetary nebulae, where dying stars are puffing off celestial smoke rings into space, remnants of stars that have torn themselves apart in the titanic explosions of supernovae, globular clusters of ancient stars that hover in a halo around the core of our galaxy, distant galaxies that are so far away it takes millions, if not billions, of years for their light to voyage the vastness of space to reach your eye. With some time and practice, you may start finding your way around the sky as well as you get around town. Knowing where you happen to be on Earth and an understanding of the celestial sphere can assist in your exploration of the sky. Like so many things in life, to know where you're going, it would be helpful to know where you are.